All right. So let's talk about rotations. So I'll get straight to the point. Turns out that a rotation in n dimensions is basically SON R. Now, what that looks like is, let's say R in Rn by n, all right, such that two things hold. One is that R transpose R is equal to the identity, and also the determinant of R is equal to 1. The first condition, actually, if you just have this, this gives you what's called ON R, and this is what makes it special. You know, this makes it special. Once you choose one, it makes it special. So this is the special orthogonal group. And in particular, you know, for example, we've already seen this for n equals 2. N equals 2, we had something like R equals to cosine theta minus sine theta, sine theta cosine theta, right? And you can easily check that R transpose R is equal to the identity, which, by the way, is just kind of a fancy way of saying that the transpose is the inverse, something which is very nice for an orthogonal matrix to have. And the fact that the determinant of R is 1 here, well, that's cosine squared plus sine squared, so yeah, it's 1. Now, why are these rotations? Like, geometrically, right? So if you have a vector v, right, and you've got another vector, let's say w, what happens when you rotate v and w? A couple things, right? So if we rotate v over here to say like that, and we wrote w over here to like, I don't know, best of my limits of my artistry like that. And so let's say that we have rotation rw for this one, right? And then this one's rv. Well, geometrically, what that ought to mean, right? Way to motivate this definition up here in particular. Well, the condition that the determinant is 1, that should keep for us the fact that, you know, we go counterclockwise to get from v to w, just like we go counterclockwise to get from rv to rw. So that's what the determinant 1 condition ought to give some sense of orientation. The other condition here actually is, well, let's see what that is. So if this angle is theta, you could call this angle, you know, theta prime, and we ought to have that theta is equal to theta prime, right? And what else should we have? Well, if it's just a rotation, rotations don't change the lengths of vectors geometrically, right? So surely the length of rw is equal to the length of w, and the length of rv is equal to the length of v. Okay, so you square those, right? Square those conditions, and when you do that, what that gives you is that W transpose R transpose RW is equal to W transpose W. I mean, in detail, fine. So, like, the way we calculate this, for example, would be RV.RV, right? But when you do that, the way that's done, dot product translates into transpose times other vector, sock shoes, right? But then this is also equal to v dot v, which is v transpose v. But the thing is that this has to be true for all possible v and w, right? So that implies that R transpose R is equal to, in fact, the identity matrix. And there you go. So that condition basically maintains the length of vectors. And it also maintains the angle, right? Because the angle between two vectors is in fact defined by the dot product. And so we'll also have that v dot w is equal to rv dot rw by the same token. That will also be the case. Okay, so that's n equals 2. We've dealt with that a little bit before. N equals 3, what is it? And so that's all you can have for rotation in 2 dimensions, right? I mean, there's no other kind of rotation in 2 dimensions because, well, it's 2-dimensional. I mean, there's no eigenvector for these either, right? Because, well, the eigenvalue's imaginary usually, right? It's complex because when you calculate the characteristic equation here, let's just do that while we're at it. The determinant of r minus lambda I, what do you got? Well, you got determinant of cosine theta minus lambda minus sine theta, cosine theta minus lambda. Okay, great. So that's lambda minus cosine theta, quantity squared, plus sine squared theta. Set that equal to 0. For those of you who know, this is exactly e to the I theta. Well, I mean, the solution then is lambda is equal to e to the plus or minus I theta, which is otherwise known as cosine theta. Plus or minus I sine theta, I should say that first, really. Oh well. And unless theta is 0 or pi, this is complex, right? So there's no real eigenvalue. Now, if theta is equal to 0, that's the identity matrix, so it's kind of a rotation, but not really. And if theta is equal to pi, well then, what is this thing? It's really just minus the identity matrix, so it's kind of, I mean, yeah, okay, it's a rotation technically, but not, I mean, it's not an interesting one per se. I mean, anyway, only those 2 very special rotations anyway actually have eigenvectors. Actually, in those cases, everything's an eigenvector, so it's kind of stupid. But usually there's no fixed axis for rotation in 2 dimensions, right? Well, there's never a special choice of axis, that much we can say. So 3 dimensions, really different. Rotations in 3 dimensions, really quite different than this. So let's talk about that. Now, you know, this problem, so what do rotations in 3 dimensions look like? It'll catch you off guard if you're not thinking about it. So we're really trying to study R transpose R equal to the identity and the determinant of R equals to 1 for R a 3 by 3 matrix, okay? And, so I'm gonna drop some knowledge on you. Lemma number 1. Well, R and R transpose have same eigenvalues. All right. I guess we could prove that. I don't know. I mean, actually, I don't think that's just something, I think that may be generally true. I'm trying to remember. Let me stay on track here. Let me not prove that. Lemma number 2. Again, these will be the gaps in my argument, although this is a little bit easier. Actually, this I do know how to prove right off the top of my head. But anyway, R inverse and R have reciprocal eigenvalues. That's actually not hard to show at all, right? If RV is equal to lambda v, then R inverse RV is equal to lambda R inverse v, pulling the R inverse past the lambda, but this is the identity, right? So what that, and then divide lambda to the other side. So what that gives me is R inverse times v is equal to 1 over lambda times v. As you can see, the eigenvalue for the inverse of R is 1 over the eigenvalue for R. And so there you have it. I suppose the proof of this is probably just that the characteristic equation is invariant under transposition, but whatever. All right, so great. Let's get back to the task at hand here. So we're trying to understand what a rotation in 3 dimensions can possibly look like. You got the determinant of R is equal to 1. So what does that mean? Well, the determinant is also the product of the eigenvalues. So let's say lambda 1, lambda 2, lambda 3. Because it's a 3 by 3 matrix, right? So there can be at most 3 distinct. And okay, I mean, yeah, fine. 2 of them could be complex, so they're not quote-unquote eigenvalues for us at the moment. They're not real eigenvalues, right? But if they are complex, they have to come in a conjugate pair. But at most you got 3 of these possibly complex eigenvalues, right? But on the other hand, you also have that, what else do you have here? You have the, well, R transpose and R have the same eigenvalues. And let's see here. Well, I guess we could say this. If lambda 1, lambda 2, lambda 3 are eigenvalues for R, right? Then what? That implies that 1 over lambda 1, 1 over lambda 2, 1 over lambda 3, eigenvalues for R inverse. We know R inverse exists, by the way, because this condition up here, well, the determinant of R is 1, so it's non-zero, so it's invertible, fine. Right, just saying. And so what I argue then is without loss of generality by lemmas 1 and 2, it must be that you can say, I mean, you can label them anyway. So you say, okay, so thus 1 over lambda 1 is equal to lambda 1. 1 over lambda 2 is equal to lambda 2. 1 over lambda 3 is equal to lambda 3. Now that actually, I mean, stop and think about it for a second here. So we're saying that the transpose, well, I mean, okay, so, fine. So this is interesting. But the thing about R inverse is, what is it here? I mean, that's the first standpoint here. R inverse is R transpose, right? So these values have to be the same as those values. Well, that's weird. Unless what? Unless lambda 1 squared is equal to 1, lambda 2 squared is equal to 1, and lambda 3 squared is equal to 1, right? But we also know that the product of them is 1, right? So, right, this is 1. So what are the possibilities, right? Well, let's see, let's just start working it out. If lambda 1 is equal to 1, then lambda 2, lambda 3 is equal to 1, right? So only real solution will be lambda 2. I guess there are really only real solution. Sorry, I'm reading something. Oh, duh. So when lambda 2, if we don't want the identity, I mean, the identity solution is what? Lambda 2 equals lambda 3 equals 1. Okay, so if all three eigenvalues are 1, then it ends up being just that R was the identity matrix as it happens. Or the other real solution, which is interesting, is lambda 2 equal to lambda 3 equal to minus 1. All right. Otherwise, as we'll see in more with more detail in future lectures, lambda 2 would be like e to the I theta, and lambda 3 would be e to the minus I theta. So, well, oh, in which case, by the way, guys, like 1 over e to the I theta, right, is equal to e to the minus I theta, and 1 over e to the minus I theta is equal to e to the I theta. So you see how the this stuff out here played out. Oops, right. See how this stuff played out in these cases. Okay, so anyway, whatever happens, right? Let's see here. You have to have one of them as 1, right? That's an inevitability. So in all the different possible cases here, I don't know if I made it terribly clear. I hope I've at least given you some idea of how you could go about giving a clear argument. So clean this up. Clean this up to argue lambda equals to 1 is always included. All right, but what does that mean? What is the significance of lambda 1? Lambda equals to 1 as an eigenvalue for a 3-dimensional rotation. Well, it's very significant because lambda equals to 1, what's that mean? That means that RV is equal to V. So, in other words, when you rotate V, it doesn't change. So what V is the axis, right? So, roughly speaking, you got some plane, maybe V is like this, right? And so the rotation is going on like that in the plane. Okay, so because the other eigenvalues take on the, either the -1 or 1, or more generally, the e to the I theta, e to the minus I theta, they have to look like that. It follows that there exists a coordinate system, all right? There exists a coordinate system where you really can just look at it as kind of like, for an arbitrary thing, let's say W. Let's say this is RW, all right, and here's W. So it's some angle rotation by theta, where if I think of V as being in the Z direction, the matrix for R, so it fixes Z and it rotates X and Y in the usual way. It looks like this. Now, I'm not sure if I've completely convinced you that this is a necessity, but so there's the piece which gives you eigenvalue 1. This piece gives you eigenvalue, well, quote-unquote eigenvalue, complex eigenvalue, cosine plus or minus I sine theta. And what I'm trying to argue is that geometrically it has to look like this in some coordinate system, right? There has to exist some coordinate system where it looks like this, unless it's something stupid like the identity transformation or the, well, I guess even if theta's pi, it still looks like this, but, this is the interesting case. Now, here's the beautiful thing. So there exists some special coordinate system where this happens, all right? Let's call that coordinate system, I don't know, beta beta. There we go. Right? But how is the ordinary standard matrix of R related? Now I'm talking about R as if it's a linear transformation. My apologies. Let's say, oh goodness gracious, let me fix this. Fix this insanity. Oh my goodness, what's wrong with me? Let's call this thing T. T. And here I mean T being the linear transformation induced by R. Okay. So what's the standard matrix for T? Well, of course, by definition, R, right? How is that related to this very special one? Well, similarity transformation, right? Okay, but the beautiful thing is this one shows you what the angle is for the rotation, right? I mean, it's there, you can see it. What are invariants? What's the same under similarity transformation? Well, I encourage you to look at the trace. You see what happens here? We have that the trace of R is equal to, well, the trace of this, right? So these guys, by the property of trace, you can move that one over there, and these end up canceling out. And you're just left with a trace of beta beta. But look at, I can calculate that straight up. It's 2 cosine theta plus 1. That's the sum of the diagonals here. But this is invariant. So I can calculate this, right? And so I get a formula for theta, basically. Theta is equal to the trace of the rotation matrix minus 1 divided by 2, right? And cosine inverse that thing. And that, folks, is a formula for the angle by which the rotation matrix rotates. Without really, I mean, and you understand this works for an arbitrary R, because we had the insight to think about, well, there just exists some coordinate system. I didn't actually go through the trouble of finding that coordinate system. That would be a pain. Because even finding the explicit eigenvector, the axis for the rotation, for an arbitrary rotation, is a pain. And yet here's the formula for the angle, just like that. Now, in 3 dimensions there has to be this eigenvector, right? But what happens when you get to 4 dimensions is, I guess, again, in 4 dimensions you could have a couple blocks like this. You get a block like this, and then another block like that of cosines and sines, right? So in 4 dimensions there doesn't have to be an axis of rotation. Well, I don't know. I'm not sure exactly what the story is in 4 dimensions and so forth. But I have read about it before, and I can point you to a book where it's beautifully described in terms of what are called the maximal tori of Lie groups. This has to do with what's called the maximal torus in a Lie group, but anyway, that made me stop talking about that, as I'm not able to talk anymore. I hope this helps you with your homework. I think it will. Thanks, guys. I shut up.